This is Unit 1, Video 6, and in this video we'll keep talking about light, and especially the mathematical relationship with light, and then we'll do some calculations. So the first thing to define is the speed of light. The speed of light is a really important constant. It has the letter C for the word constant, and think of it as probably the most important constant in all of science, which is 3.00 times 10 to the 8 meters per second. Specifically, here we have it written out to 9 decimal places, you can think, or 8 decimal places. And this is pretty fast. This is the speed limit of science, of nature. Technically you can't go any faster than this. And the question is, how far can light travel in a second? So if you have a laser and you turn the laser on for just a second, how far will that laser travel? Now usually it gets obstructed by whatever it hits, but if it keeps going, how far will it go? And for you to understand how big this number is, it'll actually go 7 times around the Earth in that 1 second, which is pretty far. So this constant is a pretty big number. You can say this is 300,000 meters per second, is what you can think. All right, here's the equation that relates the speed of light to the two ideas we talked about, frequency and wavelength. Now, I don't know if I introduced this letter right here, but this refers to frequency, and this is actually not a V. It looks like a V, but usually they write it like this. It's actually the Greek letter nu, but for our purposes we can think of it as a curvy V. Remember, this is wavelength, this is lambda, Greek letter lambda, and here you can see in the relationship that it's an inverse relationship. The way to see this is anytime you multiply two variables to give you a constant, that means if this variable goes up, this variable must come down to keep the number a constant. And that's why this is an inverse relationship. So what we can do then is we can rearrange and solve for wavelength. If we have to solve for wavelength, then we would divide frequency over, and we get speed of light over frequency equals wavelength. If we want to solve for frequency, we'll do the same thing to wavelength. We can say the speed of light divided by the wavelength equals the frequency. So these are kind of the two derived equations of the original equation. And we'll do some calculations with them. So in fact, here's the first calculation. What is the wavelength of light with a frequency of 12.0 times 10 to the 13th hertz? So our original equation again is speed of light is wavelength times frequency. So here we're asked for the wavelength, so let's rearrange the equation to solve for wavelength, which is c over this curvy v, and c is the speed of light, and it's a constant, so we'll put that in as 3.00 times 10 to the 8th meters per second. Now, frequency is hertz. Hertz has actually units of per second, so we can put that in and we'll see how it cancels out. So down here we'll put 12.0 times 10 to the 13th, and I'll go ahead and put per second. What this will allow us to do is actually cancel out the seconds, and we will be left with meters, and that's what we want for wavelength, because the wavelength is measured in meters. Go ahead and plug this in. So we got 3.0 times 10 to the 8th. We'll divide by 12.0 times 10 to the 13th, and you should get yourself a number that looks like this: 2.5, and scientific notation, times 10 to the negative 6th should be the answer. Now this would be meters, and we had 3 significant figures, so actually 2.50 to be exact. 2.50 times 10 to the negative 6 meters, and that is the answer. Hopefully that wasn't too bad. Go ahead and take a minute to do the same thing. Pause the video and try this one on your own. Alright, how about this question? Example 3 says, find the frequency of blue light with a wavelength of 480 nanometers. So in this case, we're asked for the frequency. The original equation is c is lambda times v. So here, we're asking for frequency, so we'll solve for frequency, is c over lambda. And c, the speed of light, again, is a constant, which is 3.00 times 10 to the 8th meters per second. We'll have to divide that by the wavelength. Now the wavelength is given in nanometers, and anytime you're using equations, you've got to make sure your units match. So we have to actually put this into meters. We can do a little conversion of nanometers into meters. The way you would do that is 480 nanometers. You'd begin with that. Nanometers would go on the bottom, meters go on top. We know that a meter is 1,000,000,000 10 to the 9th nanometers. So we can do this little conversion. We'll actually get 4.8 times 10 to the negative 7 meters. But what you could do to kind of shorten your work is you realize that a nano is actually 10 is 1,000,000th, which is 10 to the negative 9. That's what the prefix nano means. So what I actually do is I say, well, this means it's 480 nanometers, or 10 to the negative 9th meters. I don't know if you see what I've done. This idea right here means nanometers. And then you can simply plug this in to the calculator using scientific notation. We've got 3.0 times 10 to the 8th divided by 480 times 10 to the negative 9th. And this actually gives us an answer of 6.25 times 10 to the 14th. Now, since we have two significant figures here, technically we have to say 6.3. And then we'll do times 10 to the 14th. Now, the unit for this can either be hertz, or if you want, you can put per second. So you can do per second like so. You can even do seconds to the negative first if you would like. But all of these are appropriate units for frequency. So hopefully that made sense. Try the same thing on your own, and then we'll do a few more problems in class. Now let's talk about the energy, give you an equation for energy. Now the energy of a photon, we said, is based on frequency. We said as frequency increases, the energy increases. So a higher frequency wave down here, and think of if you were to produce this wave, say with a little paddle in the water, you'll have to use much more energy to produce this wave down here than you have to use to produce the wave up top. So everybody visually kind of sees that this wave has more energy. But there is a mathematical equation for this, and the equation says E, which is referring to the energy, is equal to h v. Now this v again is the frequency. It's actually nu. It's the Greek letter nu. Now the energy that we'll be using will actually be in joules. We've introduced joules as a unit of energy. Frequency, again, it could be in inverse seconds, 1 per second. And then h, this business here, is what's called the Planck's constant. Now, you should get used to the fact that every equation has some sort of constant in it, and the constant is there to actually tie together the two variables that you're dealing with. In this case, what you'll see is the relationship between energy and frequency is direct, which means if you increase the frequency, the energy will actually increase, because you're always multiplying by a constant. Now the constant, Planck's constant, we use the letter h for Planck's constant, is 6.626 times 10 to the negative 34 joule seconds. You don't have to memorize this constant, it will be given to you, but you'll realize that this constant contains joules, which is energy, and it contains seconds, which is frequency. So it ties together the idea of frequency and energy together. Now joules, here it says joules has basic units, subunits of this, and this will be important in an equation that's coming up, and it's kilograms meters squared per second squared, because remember there are really about 5 basic units where everything else is derived from. And this is a picture of Mr. Planck, Mr. Max Planck. So feel free to get a poster and hang it in the appropriate place. So here's an equation, or here's a problem we can use to, here's a problem we can do using the equation. What is the energy of a photon in kilojoules that has a frequency of 8.3 times 10 to the 14 hertz? So really we're just asked to find energy, and the equation is E equals h nu, or h is a constant in this case, so 6.626 times 10 to the negative 34th joule seconds. We get to multiply that by our frequency. Now our frequency in this case is 8.3 times 10 to the 14th. So 8.3 times 10 to the 14th hertz. And what I'll do is I'll put it as per second, because hertz are per second. And you simply end up multiplying those two numbers. So we got 6.626 times 10 to the negative 34th times 8.3 times 10 to the 14th. And what you'll get is you'll get the energy of 5.499, get 2 sig figs, so let's do 5.5 times 10 to the negative 19. Now the unit for this, since seconds cancel out, is joules, and that's what energy is referred to in joules. Now this is a really tiny number. Notice 10 to the negative 19th, which makes sense because we are talking about a single photon, a tiny particle. Remember, a photon is like a tiny little particle of light that's flying through space. Right, now we want this in kilojoules, so to go from joules to kilojoules, kilo means 1,000, but be careful, make sure you say that 1 kilojoule is 1,000 joules. You end up dividing this number by 1,000, 3 orders of magnitude, and you actually get 5.5 times 10 to the negative 22nd joules. So you'll become 3 times smaller, 3 orders of magnitude smaller. And this is the energy of a single photon in kilojoules. Go ahead and take a moment and answer this question using the same equation. And looks like we're missing here it comes. So the wave nature of light. Now, scientists realized that, well, if light has this dual nature of having material properties, if we can think of light as particles, matter should exhibit wave properties, which was a strange idea, but this turned out to be true. So in fact, matter can actually be thought of as a wave. Now, as you'll see, this will only apply to tiny particles of matter, like electrons, like protons. Protons are quite a bit bigger. Neutrons, these are protons, neutrons. You can actually have whole atoms. You can have a hydrogen isotope, for example, or an isotope of hydrogen, an isotope of oxygen. All these will be small enough to have a wavelength associated with them. And the equation for that is this equation here. Lambda is the wavelength. The wavelength of all matter equals h, this is Planck's constant again, that's defined as Planck's constant, divided by m, which is mass. Now this will be mass in kilograms, and the reason why it's in kilograms is because joules is defined in kilograms. And V here now is not new. This is actually the real V from physics, which is meters per second. This is V as a velocity. So this is not new that we've been talking about, not frequency. So don't confuse those two. They could have used a better letter, but here we are. So we're actually going to use this equation now to talk about matter having a wave property. And where this is applied is with electrons especially, because electrons are definitely matter. They have a mass, but they're so tiny that they actually move around the atom in a wave. So if you think about the atom, here is the atom. We have the electron cloud going around the outside, and you can think of the electron cloud going around side now in a wave. It has a wave-like property, and because it's tiny enough. Now, this idea is not only true, but it's also used practically, and they've actually made a microscope based on the electron. And this allows us to see much deeper than the visible micrometer range that our human eye can see. We can actually go deeper into the nanometer range because of this. And you'll see that this is because the wavelength of an electron is much tinier than a nanometer, which means we can go deeper, which is great. Now, this idea is applicable to any object, technically even a basketball or something. I guess that would be a softball. So, but the frequency of a big item, a big piece of matter, is so insignificant that we can technically ignore it. But it is significant for things like electrons. And here's an electron microscope picture of some viruses. And you can actually look up some electron microscope pictures online and see some pretty neat things down in the micro world. So here's an equation for an example. What is the wavelength of a hydrogen atom moving at a velocity of 5.97 times 10 to the 5th meters per second? So now we're going to apply the third equation that we saw, which is wavelength is h over mv. Mv, by the way, is called momentum in physics. Mass times velocity is the momentum of a particle. So we have h, which is a constant, which is 6.626 times 10 to the negative 34th joule seconds. On the bottom we have mass. Now, we're not given mass, we're given a hydrogen atom. So we have to do a little bit of math to get the hydrogen atom. Now, we'll have to get the mass. Now, it has to be in kilograms. the mass here has to be in kg of a hydrogen atom. So we'll have to do a little conversion from a previous lecture. So we have 1 atom of hydrogen. What we'll do is let's go ahead and convert from atoms to grams. Now we'll have to go through moles first, and then we'll have to go from moles into grams. And actually, because we'll have to go to kilograms, we'll go from grams to kilograms. So this is just a conversion from atoms to grams. We know that a mole has 6.02 times 10 to the 23rd atoms. This is Avogadro's number. And we know that a mole of hydrogen, if you take a look at hydrogen in the periodic table, has a mass of 1.01. And again, this is hydrogen. Element number 1 has a mass of 1.01. Remember, this number here refers to the mass of a mole of that element. And then again, from grams to kilograms, you know that 1,000 grams is 1 kilogram. So let's go ahead and calculate this down here. See what we get. So if we do 1 divided by 6.02 times 10 to the 23rd times 1.01 divided by 1,000, we'll actually get ourselves 1.678 times 10 to the negative 27. This would be kilograms. Now this is how heavy a tiny hydrogen atom is. Not very heavy at all. And by the way, I'm using 4 sig figs for now, and we'll cut it down to 3 in the end. This number does not limit me. This is an exact number. Okay, now we can go ahead and plug this into our original equation because we've got mass. So 1.678 times 10 to the negative 27 kilograms. And then our velocity has to be in meters per second, and it's already in meters per second. We're good to go. 5.97 times 10 to the 5th meters per second. All right, go ahead and take a moment with me to calculate this. 6.626 10 to the negative 34th divided by 1.678 10th to the negative 27, and then also by 5.97 times 10 to the 5th. What you get here is 6.61. We got 3 sig figs times 10 to the negative 13th. Now the unit here will actually be meters because we're calculating wavelength. Wavelength is expressed in meters. And technically the seconds cancel out, and then there's seconds in joules, which cancels out with the kilograms in joules, so you are left with meters. So this is the answer to the problem. So a hydrogen atom going that fast actually has a wavelength, and this is quite small. This is actually smaller than a billionth of a meter. This is actually smaller than a trillionth of a meter. This is actually 0.6 trillionths of a meter, which is pretty tiny. That wavelength is really, really small of that wave. It's really, really hard to see, but you can actually measure it, and it's significant enough. All right, so this will go ahead and pause the video, try this question on your own, and hopefully make sense. This will end the 6th video of Unit 1.